SwayamPrabha. Digital India. Educated India.
Welcome to the NPTEL online certification course on structural systems in architecture. Today we are in the module 3, the third week. The topic of the module 3 is structural mechanics, and today is the lecture number 12, the second lecture in this week, and this is on the bending stress in beam part 2. So, in this particular lecture, we will these are the typical concept that will be covered. If you remember, we have developed already the stress curvature relationship in our first lecture, and we will try to solve one small numerical examples from that, and then we will again going to find out another relationship in the bending theory, that is the moment curvature relationship, which is one of the very important the relationship in the this bending theory, and that particular moment curvature will take you to till the last in the design stage. We will do some kind of a bending equations, and based on that and numerical examples will be solved, and we will see some of the concept like the sectional modulus and the advantages of the hollow sections. So, the learning objective of this thing is very clear cut, and we have to apply the theory of bending stress in the structural engineering. So, if you see the how basic things in the structural engineering can mobilized by this equation of bending. So, if you remember, these are the two slides I have taken out from the previous slides. Is bending stress distribution that depend upon because of the external loading, the beam is going to bend. Either if it is simply supported beam, it is a sagging, and if it is a cantilever beam, it is going to be a hogging kind of a moment. So, depending upon the bending, it is going to rotate each and every sections which is going to rotate, and that rotation gives you a kind of radius of curvature at a certain point of the above or maybe the below. So, these are some of the assumptions of the bending theory, and we also derived this particular radius of curvature versus the stress equations like this, if you remember. Now, we will spend some 2 minutes here. The E, as you know, it is the E is the Young modulus of elasticity, that the material property, right, this Young modulus. The R is the radius of curvature. So, if the beam is something like that, it is bending like this, that means this R is the center line of the beam, which is the neutral axis or the neutral plane, you may say. This is called the neutral plane. So, from this neutral plane, definitely there is a circular, we will assume that this is a purely circular. So, this is your R. So, this is your radius of curvature, and this is your center of or curvature. Okay. So, these two are sometimes it is difficult to find, and we may not sometimes require to find out this particular R, but this sigma and y is very important. Sigma and y is property of the particular each and individual sections. So, if this is the elevation of the beam, so if I take this section is nothing but a cross section like this, or maybe if it is a T section, so something like this, or maybe this is the I section, so this is something like any kind of a section. That is why we required, and those kind of sections, the values of the IXX and all those values. And what is this Y is that it has a neutral axis. Then what is neutral axis? Where the stress is equal to 0. So, stress is 0 over here, stress is maximum at the top, stress is maximum at the bottom also, and 0 over here. So, this is the distribution of the stress. So, if I want to find out the each stress in the each layer, I need to know how much is this Y value. So, Y is the depth of the particular layer where you want to find out the stress, right. So, suppose if it is a kind of a section like this, You know this is the CG, that is why CG is important to find out, because you have to find out the y from the CG. This is your CG axis, okay, and this is, suppose you want to find out the how much is the stress. You know the stress will be definitely 0 here, CG, but this is maximum and it will flow like this. But if you want to find out the stress, this sigma, you need to know the this y, put the y value. So that is why you require the value of the CG. You need to know the CG, and from there you have to go up and down. And if it is a sagging kind of a moment, this is sigma c and this is sigma tensile. So this is the, in a nutshell, this is the stress curvature relationship. Now there is a small numerical problem. A straight steel scale is bent by 120-degree angle, and so something like this, I am going to bend it. So I have to find out the how much is the stress. So I have found out the R value by because this is your 120 degree. So this is half of this is 60 degree. So with Pythagoras I can find out the how much is this, or trigonometry. So and now I can use this formula. I know the value of R, I know the E is given. If it is not given, you can take 2 into 10 to the power 5 is the value of E. Please note that this is the R value, and the sigma is your the stress value at 1.5 mm, because I want to find out the stress in this particular steel at the topmost point. The thickness is T is so this is the scale, suppose, and if this is the 3 millimeter is the thickness, and this is whatever may be the length. The CG will lie at here, and the topmost portion is your 1.5. So that is why this 1.5 is taken into account to find out the maximum stress which will be occurred in the top. So that is this much. So now let us go to that important one, the moment curvature relationship. Now as we know that a particular section will have a neutral axis NA, and the neutral axis, above the neutral axis will be some compressive kind of a stress, which is I have shown here in the green color, and the below it is a tensile kind of a stress, which I have shown in the blue color. But this drawing is not very perfect, it has to be something like both has to go like that anyway. So let me erase this one. So this total compressive force, compressive stress is applied over area above neutral axis. Maybe it is varying from 0 to some value, but in totality it will give some kind of a compressive force if it is having a application the area to apply for, and there is a stress value. Similarly, the total tensile force is also going to be evaluated because it is below the neutral axis, and you know the area below the neutral axis, you know the variation, so you can find out what is the tensile force in the neutral axis applied over here, and this will be separated by a distance called the river arm, and these two are the equal and opposite force, it will create a moment. So somehow I can find out this particular moment which is actually generated because of the applied force and the moment. So that is called the moment of resistance of the section. So now I will assume that there is a small area dA which is at a distance y from the neutral axis. See, this y is very important. I have just now calculated what will be the stress over there, and suppose the stress over there is F. So I can just project it in my this particular the stress distribution curve and find out that is the stress. So I may say that this force at this elementary area is nothing but F into dy. The stress into area is the compressive force or the whatever may be the tensile force or so. So as I have assumed that at this particular y, the stress, this much stress is your F, and this is the area which is almost at a distance y. So this is the small force, elementary force, and the moment created by this elementary force above the neutral axis, about the neutral axis is the force into the distance. So this force and distance is the y. So it is F dA into y. So now the sum of all such small, now if you just sum all the forces of this, and you can just accumulate all the sum of these forces, you can find out the total moment of resistance of the sections. So, that is why I have written this sum of from y bottom. Y bottom is this bottommost portion, y bottom, and this is the topmost portion, so y top. So, please remember this y, which is layer distance, has to be calculated from the CG axis. So, throughout from bottom to top, F into dA into y is nothing but the moment. Now, this has to be again you have to be a little bit of derive. So, F I have changed because I know the sigma by y equal to E by R. Please remember, this is your stress curvature relationship. So, from there this is the F. So, the E by R into y, I replace the value of F like this, or stress like this, and so this E by R goes out. So, the y remain, and this is dA into y square. And if you remember dA into y square, last class what we have seen, that I, this is the moment of inertia, is nothing but the summation A into y square, or the area into y square. So, finally, it is come down to m is equal to E by R into I, moment of inertia. So, the moment curvature relationship with us. Now, m by I will rearrange this, m by I equal to E by R, the moment that created, or the moment, the external moment created by the external loading by the sectional property, the I is equal to E by the radius of curvature. So, the final bending equation comes like this. This is very important, very important, and this particular equation is the first part of this equation is also very important, because we require this equation everywhere in our structural engineering to find out the stress to design the beams and all. So, here you see the external moments are the m, the moment of inertia is the beam cross sections, and the moment r is the radius of curvature, and the E is the Young modulus of elasticity, and sigma is the distribution, this is a spelling mistake, of the bending stresses over the depth y from the neutral axis. This is very important. This is the neutral axis, this is the section, this is the neutral axis NA. So, you need to know the stress distribution is like this, and stress distribution anywhere, any stress you want to, or topmost stress or any. So, you need to know this vertical value of y, and correspondingly this sigma will be appear in your equation. So, if you put the moment, external moment of the resistance or so, you will get. So, suppose it is a simply supported beam, and this is the bending moment diagram of the beam. So, you know this is the beam cross section, suppose it is the rectangular cross section. So, at the center of the span, you know it is the bending moment is high, very high towards the span, and the distribution will be something like this, and anywhere near to the support the bending moment is low. So, if I remember the m by I equal to sigma by y. So, m is equal to low, but I remains same. So, sigma, the distribution of the sigma also will be smaller, because the effect of m is smaller over here. So, this triangular distribution of the sigma, this is the stresses will be high in very near to the support. Similarly, in case, so I can go something like that, I can think of beam making like that the central portion has to be thicker. If you make it thicker, your I value increases, so you can create a better way to support the particular stress. Similarly, in case of the cantilever beam, this is the bending moment diagram, and if you are very near to the fixed end, so the bending moment is very high. So, the distribution, the stress distribution is high, but here if you remember, I have written sigma c in the bottom, that means compression in the bottom and tension in the top, because a cantilever beam will bend like this, right. So, in that case the tension comes top and the compression comes bottom. And in the free end, see, you see the bending moment is very less. So, that is why the stress distribution topmost fiber and the bottommost fiber also will be very less, right. And that is why I need to have a small depth and in the free end, but the larger depth in the end and in the to encounter this kind of rotations and the moment also. So, I have a small numerical example to understand this particular bending equation. I have a beam of 6 meter and I have two buckets of water. Each bucket contains 1200 liters of water and they are placed 2 meter apart. Now 1200 liter water is approximately equal to 12 kilonewton. So, I replace this 2 bucket of water by 2 pointed load of 12 kilonewton. So, it gives me the maximum bending moment at the center. So, it will be actually the bending moment will look like this, a trapezoidal case, trapezoidal distribution, and the M max will be 24 kilonewton meter. It is PL by 3. So, 12 into 2. And let us suppose the beam cross sections is this 300 depth and 120 is wide. So, I know that I value of this thing 1 upon 12 B d cube is this much, and the y is 150. Why? Because the top, this is the CG axis is the center, and this is the y, or the y max at this 150 is the maximum y value, and that gives you the maximum stress value. I am to find out the stress at this particular topmost fiber. So, I put this in equation m by I equal to sigma by y, sigma equal to m by I equal into y. So, m equal to E is equal to 24 into 10 to the power 6, because here I have written it in kilonewton millimeter. This is in millimeter to the power 4, 270 into 10 to the power 6, and this is also in millimeter. Okay, this y value. So, I found that the sigma is 13.33 Newton per mm square. But let us suppose that the permissible bending stress of the beam material is only 10. So, it can only be a 10 Newton per mm square. If you put those loads, it is 13.33, it is more than 10, not more than permissible, it is going to crack, it will go to tear. So, what is the solution then? So, at the present condition of the beam under bending stress is 13.33, beam will going to fail at this present condition. So, what are the solutions that we have to make the structure safe? So, let us see the bending equation. So, what I have to do? I have to reduce this sigma, right? Sigma, if I want to reduce, so it was 13.33, I want to reduce it to minimum 10, not more than 10, because 10 Newton per mm square is the permissible. Now, I can increase the value of I, that is definitely decrease the value of sigma, or I can reduce the value of m. So, there is two way out. So, there are some solutions available. Reduce the load, yes, instead of 1200 liter, you can put some less amount of water, or rearrange the position of the bucket. That also sometimes maybe you can you can go through like that, and the movement will be less. Or increase the depth of the beam section. If they increase the depth of the beam sections, the I will be increased, the moment of inertia, because it is d cube, right. So, the first one we will go like that, reduce the load and decrease the amount of water in the bucket. So, I have those things are all like the previous, but the sigma permissible is now 10. So, now I put over there and then found out that the m should be not 24, but 18 kilonewton per meter, because the I value I have given as it is, y value as it is, but instead of 13 this is 10. So, now I found out that the maximum bending moment for that will be the 9 kilonewton will be the load instead of 12 kilonewton, if you remember. So, that means that 900 liter has to be the weight of the volume of the water. So, I have written down the solution number 1 as this is by typological error. They reduce the load by decreasing the water in bucket. Each water should have not 90, it should be 900. I will just do it in when I upload this PPT, I will rectify those mistakes. It has to be 900 liter of the water can be the maximum. Now, the rearranging the positions, now I know that will be the 18 kilonewton per meter, but I know that this is 6 meter of the beam. So, let us go put this to 12 kilonewton little farther away. So, let us assume that this is x meter from the support. So, I can find out the moment equations and find out the value of x is as 1.5. So, what I have written here, move both the buckets 0.5 meter towards the support, such a way that it will give you less number of Initially, if you remember, it was 2, 2, 2. Now it is 1.5, 3, and 1.5. That gives you the bending moment. It will be a again it will be a the trapezoidal, but this bending moment instead of the 24, it will be 18. So I have pushed little bit towards the support. So that is a rearrange as the position of the bucket, but I have kept the same 1200 liter, not 900. Then they increase the depth of the beam. There is another solution, we can increase the depth of the beam. So we will use this equation, and let us suppose the new depth of the beam is d. So I have put all the values 1 upon 12, 120 into d cube, 120 remains same, that is the width of the beam, and d by 2. So finally I found out the equation and solved for the d, and the d value of d comes like 347 millimeter. So my third options will be, solution option will be, increase the depth of the beam from 300 to, it was 300 millimeter. So it was 347 millimeter. So that is also another solution. So we have to now go to the concept of the sectional modulus. Now sectional modulus is one of the concept, because in that particular equation you see this Ixx and y are the property of the section. Okay. Now you know that maximum sigma will be encountered at the topmost layer, where this is your y max. Okay. So y max by I. So if I rearrange now, the m equal to Ixx by y max into, if I write here y max, then it will be the sigma max. So this Ixx by y max is called Z, or the sectional modulus. Okay. So in case of the rectangular section, I know this is the Ixx 1 by 12 BD cube, and y max is d by 2, because CG will lie exactly at the center. So d by 2. So the Ixx will be 1/6 of BD square. So suppose there are some symmetrical sections where your y max and the y bottom, y top and the y bottom will be equal. So y max is a single value. So it has, I know this will be the xx, the CG line will be exactly at the center in all the cases, because it is symmetrical kind of a beam. So I know this will be my, this will be my, suppose in this case this will be my y max. This is also another y max in the bottom, but both values are same. If the both values are differ, we will see in the next lecture what we will going to, how to handle that one. So these are the y max. So I can, if I know the I value, I can easily compute the what is the. So suppose the sectional modulus, if I want to find out for this circular sections, it is d, and this is also rectangular section, which is d by d. So I know this is the value of the z axis. So z axis for the circular is this is the Ixx for the circular sections, and this is d by 2 is the y max. So this is 1 by 32. I did a blunder over here. This has to be pi. So this has to be pi by 32 d to the power cube. Similarly, in case of this square sections, this is z square is 1 upon 12 d to the power 4 and d by 2. So 1/6 d to the power 3. So now these two are maybe compared, and then we can find out that what is the moment is z into sigma max. So the moment of the moment of resistance of the square by rectangular will be the z square by the circular, because the sigma max will be same for a same type of material. So here it is 1 upon 6 square d cube, and this is again this mistake is carry forward, pi by 32 d to the power 3, and so I will recalculate and tell you this value. So this is not the true value. Okay. So this will be the ratios of the moment can be can be found that in the square sections and the circular sections. Now we can find out a particular I sections which is having a area of cross sections like this, and we have a Ixx like this, and this is equal. I mean, this is the symmetrical kind of I sections. The CG distance is 60 millimeter above. So the y max is this 60, and the suppose sigma permissible is your 250. So Z is 89800, that comes from this Ixx by Y max. Ixx is this, Y max is this, and the moment of resistance of the beam is suppose 24.45 kilonewton meter, because this is your Z into this is sigma permissible. From there I can find out this is the moment of resistance of the beam. That means this much amount of moment can resist. So if that beam, that particular sections is applicable over a span of 6 meter, so I can say this is maximum bending moment at the center, as you know it is WL square by 8, which has to be maximum 22.45 kilonewton meter. So I can find out that for a the 6 meter of L is your 6 meter, so it is 36, and so this is 5 kilonewton per meter is the maximum UDL, the uniform distributed load you can put. If it is in the 6 meter long cantilever beam, this is again a printing mistake, this is a cantilever beam. So the bending moment will be WL square by 2, and this will be your 22.4, and then this is going to be your 36, L is, so this is only 1.25 kilonewton per meter loading it can be resist. So in case, what is the advantage of the hollow sections, let us see. So suppose I have a square sections of dimension 40 by 40. So this gives me the area of 1600. This gives me the I value of almost 213 into 10 to the power 3 millimeter to the power 4, and the sectional modulus is this by 20 y 20, because the y max is 20, because the section is 40 depth 20. So this is the I z of this particular beam section. Now let us say there is a hollow sections which is having the outer dimension is 85 by 85 and the inner dimension is 75 by 75. Very interestingly, if you find out the area remain the same. You see, this and these two are the same. So you have same amount of material you have used for both hollow and this particular the solid. But moment of inertia is, if you remember in the first lecture, the first minus second. So moment of inertia is increased a lot. It was 213 10 to the power 3. Here it is 1713.3 10 to the power 3. Almost how much? 8 times. 7 point sometimes has been increased. The sectional modulus of the beam is this 173 by this I value by this 42.5. Why 42.5? Because the CG is here, and from here to here it is half of 85. Half of 85 is your 42.5. So this is your the value. This is your Z value. So if you go to the validate that which section is better for strength purpose or so. So say both are having same area. There is no question of that. But the solid one is having the Z value of 10 point something in 10 to the power 3, whereas the hollow one is having 40 point, almost 4 times higher Z value. And why Z value is important? Because Z into the sigma permissible is the moment value. So the moment is Ixx, that Z Ixx by Y max, which is your Z value into the permissible. So the hollow by solid, if I want to compare the moment of resistance of the hollow by solid, so I will not take the sigma permissible here, because I am assuming that both are the same material, same steel or maybe same concrete or same timber. So that is why the sigma permissible for hollow and the sigma permissible for solid is going to nullify each other, because sigma permissible is the material property, it is due to the material property of the beam. So both are having same material, it will nullify. Hollow and solid, that gives you the symmetrical property of the beam. So that is why the Z value is very important. So the ratio of that gives me 3.77. So I must say that the hollow is 3.77 times better than the solid from the strength point of view, but both the cases you are consuming same amount of material. So, the same cross section area, same weight, same and material, but the hollow section can take 3.7 drive higher moment. Therefore, the beam with hollow sections is far more effective than a solid section. So, that is one of the concluding thing what we have understood. We have taken this reference for this particular presentation. In the conclusion, I must say the banding theory and the bending equation plays a vital role in the structural engineering applications. Beam sections need to be chosen suitably to take effective material for the use or so. And I have some homework for you. The beam, one beam is given as a depth of having 30 centimeter depth, and the I value is given to you. So, you have to find out the maximum UDL and the single concentrated load if the permissible stress is 110 Newton per mm square. So, this is another problem. So, this problem you just go through. 6 meter long simply supported beam is having, I have marked AB, a line which is the length of the line is 30 millimeter, and this line is decreased by 0.03 millimeter when it is applied by the load, and this is the central line of the beam. This is the mid depth is about 75 mm above below this line AB, and this is a rectangular cross section of 60 mm width by 200 mm depth section. So, you have to find out the stress at the topmost layer of the beam and the magnitude of the imposed UDL, how much UDL it can take. So, thank you. This is the end of the lecture number 12.